This is number 46 in chapter 16. It basically asks us what is the mass of ammonium chloride should we add to 2.5 liters of a 0.15 molar, 0.155 molar ammonium solution. To obtain a buffer with a pH equal to 9.55. So we're trying to create a buffer. We have our parent base. We have a concentration for our parent base. And we want to know how much of the conjugate acid form, in this case ammonium chloride, do we need to add to reach a pH of 9.55 for this particular buffer. So there are two ways to go about this. We can use the ice table, and that's how I'll start the question, but then I'll follow it up with using the Henderson-Hasselbalch to show you that we could also use that equation as well. And so to begin, we always want to write the buffer equilibrium according to the parent. And so in this case, our parent is the NH3. And so that NH3 is going to act as a base and make NH4 the conjugate form. That means we have a Kb which is equal to our products over our reactants. Again, we're going to have to look up that Kb. I'll come back to that in a second, but let's look at our ice table. And so here we're really looking for an initial concentration. We know our NH3 concentration is 0.155, but what we want to know is that. We want to know why. We want to know the initial concentration of our NH4 so we can actually then figure out the mass. Our hydroxide we begin with is 0, but we do know what the change actually is, right? As far as x is concerned, our plus x and our minus x. We know what x is because we know what the pH is. So the first thing we have to realize is that this is pH, so that deals with H3O plus concentration, but in our column we have hydroxide. So the first thing to do is to convert that. So if our pH is 9.55, then that means our pOH must be 4.45 from our pH, right? Remember, they both relate to 14. And so I can figure out that hydroxide concentration by taking 10 to the negative pOH, or 10 to the negative 4.45. And that gives me a hydroxide concentration of 3.548 times 10 to the negative fifth. So that's my hydroxide concentration, 3.548 times 10 to the negative fifth. And so I want to take that value and subtract it from my 0.155. Then when I do that, I get 0.1549. And then for this value, we're going to have this y plus that 3.548 times 10 to the negative fifth. So we know these equilibrium concentrations, we still don't know why, but when we substitute into our KB expression, we can actually solve for what that y is. So let's go to that. So our KB, if we go to our table, is 1.76 times 10 to the negative fifth. So that's from their table. So we got to have that value. And so that's going to be equal to our y minus our 3.548 times 10 to the negative fifth times that again, that 3.548, sorry, I'm running out of room here, times 10 to the negative fifth. So let's start that again. Let's try to make a little bit more room here. I'm going to have to erase this ice table. And so again, just to reiterate, so our KB is 1.76 times 10 to the negative fifth. That's going to be equal to our concentration of our ammonium, which is the Y plus that change, 3.548 times 10 to the negative fifth, times again that 3.548 times 10 to the negative fifth. That's going to be all over our 0.1549. So again, we got those values from the ice table. I'm sorry I had to erase that, but we can solve for what y is going to be if we do some rearranging. If we bring our 0.1549 over, we get this value. And then if we multiply the 3.548 times 10 to the negative fifth throughout this, we then get these two values, our 3.548 for y, and then we have 1.258 to the negative ninth. We isolate our terms and solve for y. We would get 2.725 times 10 to the negative 6 when we bring that 1.258 over to the other side, and then we want to divide by our 3.548 to isolate what y is, and we get that to be 0.0768 molar. So basically, again, this is kind of like chapter 15. We're trying to find an initial concentration, but since we're given the pH, we know the change, and so we can actually work backwards through the ice table. So that's our molarity of y. It still hasn't answered the question yet as far as our mass, but we can go from there. So if we take what our y is, that's at 0.0768 molar, we can then just do a conversion. The 0.0768 moles per liter. We can then use our volume of 2.55 liters to get into terms of moles, and then multiply that by the mass of the ammonium chloride, which is 53.45 grams, to get us 10.26 grams of ammonium chloride that is needed to make this buffer that has a pH of 9.55. The other way to look at this is to look at it by way of a Henderson-Hasselbalch equation. So our Henderson-Hasselbalch would be POH equals PKB plus the log of my ammonium over my ammonia, or the log of my conjugate over my parents. And so what we want to know is, what is that NH4 concentration? So we can actually rearrange this, right? So if we take our log and isolate it, we get this. We have POH minus PKB is equal to that log, right? We're just taking PKB to the other side. And then if we get rid of the logarithm, we would get this, that we can take the base 10 to get rid of the logarithm, and then we have base 10 of that quantity, or that difference rather, of POH minus PKB. And so if we plug these in, if we come up to here, right, our NH4 concentration is what we are looking for, but we have that initial concentration of my NH3, and so that's going to equal 10 to the POH. We already figured out the POH, which is 4.45, minus the PKB. Now you'd have to take the negative logarithm of that KB. Remember, our KB was 1.76 times 10 to the negative fifth. So we got to take the negative logarithm to get the PKB, which is actually equal to 4.75. And so when we solve that, when we bring our 0.155 over to the other side and we do our base 10, we get a ammonium concentration to be equal to 0.0776 molar. And in the first part of this, remember, the first concentration I got was 0.0768 molar. So again, what I'm trying to say here is that you can use the ice table to solve for these types of buffers with the Henderson-Hasselbalch. We got 0.0768 molar for that concentration, and then we went further to actually get the mass, but that is our concentration we got from using the ice table. And then when we use the Henderson-Hasselbalch, we pretty much got the exact same value. So you can use either to solve these questions. That's number 46 in chapter 16.